Now let's look at the second example. This is similar to the first example, but now the length is only L, and the point that we want to find is above the end of the rod. And for this example, the line charge density is constant, it equals to lambda. And again, we are going to find the net electric field at point P. Here's a sketch of the problem. We have a rod with length L, and the point P is above the left end of the rod. The distance from the rod to point P is y, and the density is constant, it is lambda. Similarly, we are going to break the rod into small pieces. For example, let's focus on this element. This dq equals to lambda times dx, where dx is this length, dx. And the blue line represents the distance from the element to the point P. Let's call this r, and let's call this angle theta. Unlike the previous example, there's no symmetry in this example, so the total electric field will have x and y components. So we have to find both. Let's first look at the x component. Ex, it equals to integral of dEx. So we sum up the x component of the electric field from each small element, which equals to integral of Coulomb's constant times dq divided by r squared. And since we are focusing on the x component, so we have to times cosine theta. And we are going to use a similar trick. We draw a triangle. This is my x, this is my y, and the distance from the element to P is r. Using Pythagoras theorem, it equals to square root of x squared plus y squared. And this is my theta. So cosine theta equals adjacent over the hypotenuse, which is x over square root of x squared plus y squared. Then we can substitute the r and cosine theta into the integral. So this equals integral of Coulomb's constant, and dq is the density times dx, divided by r squared, which is x squared plus y squared. Then times cosine theta. Cosine theta is x divided by square root of x squared plus y squared. So again, the x squared plus y squared is the r squared, and this thing is cosine theta. And we are performing the integral from 0 to L. Now we have the integral set up. Then we simply need to solve this integral. We can pull out the constant. We have Coulomb's constant and the line density, lambda, times the integral x over x squared plus y squared to the power of 3 over 2 dx from 0 to L. This integral is similar to example 1. We use u sub. Let u equals to x squared plus y squared, so du is 2x dx. So this equals, we borrow a 2 from du, so at the front I have to divide it by 2, times Coulomb's constant times the density times the integral u to the power of negative 3 over 2 du, and integral from x equals to 0 to x equals to L. This equals half Coulomb constant times density times u to the power of negative half divided by half. And we substitute the u back, we get x squared plus y squared to the power of negative half divided by negative half from 0 to L equals, the half cancels out with the half in the denominator. So negative of Coulomb's constant times lambda times 1 over L squared plus y squared minus 1 over y squared. In a quick note, since the rod is positively charged, So the electric field will be pointing away from the rod. So for this element, the electric field will be upward. For this element, the electric field will be pointing this direction. And for this element, the electric field will be pointing in this direction. So you can see that all the x components are either 0 or negative. Here we are only computing the x component of the electric field. So if you run it in vector form, you have to remember to add a negative sign in front, which will cancel out this negative sign. Now let's look at the y component. Similarly, we are going to use integral. We are going to sum up all the y components of the electric field from each element. So Ey equals to integral of dEy, which equals integral of Coulomb's constant times dq divided by r squared times sine theta, because here we are looking for the y component. So same approach as the Ex. We substitute dq, which is the density times dx, and we substitute the r squared from our triangle. R squared is x squared plus y squared. And we also substitute for the sine theta, which is the opposite over the hypotenuse. So this equals integral of Ke, Coulomb constant, times dq, which is lambda times dx, divided by r squared, which is x squared plus y squared, and sine theta is the opposite divided by hypotenuse. The opposite from our triangle is y divided by hypotenuse, square root of x squared plus y squared. And the integral goes from 0 to L. We pull out the constant. We have Coulomb's constant, lambda, and y. Y is the vertical distance to the point, so it is also a constant for this integral. Then times the integral dx divided by x squared plus y squared to the power of 3 over 2 from 0 to L. Now we cannot use the u sub since in the numerator we don't have the x. Do you remember from calculus 2 how we compute this type of integral? So you can note that here we have x squared plus y squared, which is the x squared plus a squared form. When we have this form in the integral, we use trigonometric substitution. So we are going to let x equals to a tangent theta, and the a here is y. So x equals to y times tangent theta. So dx is y times secant theta squared, d theta. Then we substitute the x and dx into the integral. We get Coulomb constant times lambda times y times the integral. Dx is now y times secant theta squared times d theta. In the denominator, we have x squared, which is y squared times tangent theta squared, plus y squared, and whole thing to the power of 3 over 2. And this is for x equals to 0 to x equals to L. Then we are going to use the trigonometry identity. Tangent theta squared plus 1 equals to secant theta squared. And we get this form when we factor out the y squared. So this equals Coulomb constant times lambda times y times the integral y times secant theta squared times d theta. In the denominator, we have y squared, then to the power of 3 over 2, that is y cubed. Then times tangent theta squared plus 1, which equals to secant theta squared, and to the power of 3 over 2. Or we can rewrite this as secant theta to the power of 3. So secant theta cubed. We cancel out a y, and we cancel out a secant theta squared. And this integral is from x equals to 0 to x equals to L. this equals Coulomb's constant times theta times y integral of 1 over y and 1 over secant theta. 1 over secant theta also equals to cosine theta. And this is for x equals to 0 to x equals to L. Then we can substitute the cosine theta. From how we define here, we have tangent theta equals x over y. So if we draw a triangle, here's the theta. Tangent theta is x over y. So the opposite is x and adjacent is y. Then cosine theta would be adjacent divided by hypotenuse. The hypotenuse here is square root of x squared plus y squared. And we know that integral of cosine theta equals to sine theta. So this equals Coulomb's constant times lambda times y. And the result of the integral is 1 over y squared times sine theta. Then we use the triangle in red to replace the sine theta, which is opposite divided by the hypotenuse. So x divided by square root of x squared plus y squared. And integral goes from 0 to L. Then I pull out the 1 over y squared. This equals Coulomb's constant times lambda divided by y times, I substitute x equals to L. So L divided by square root of L squared plus y squared. And that is the magnitude for y component. Then if we combine everything, we get the net electric field from the line, from the rod, equals. From the diagram, we know that the x component would be negative, and the y component would be positive. Since the rod is positive, so the electric field would be pointing away from the rod, and that will give us a positive y component. So the net electric field equals Coulomb's constant times y times 1 over square root of L squared plus y squared minus 1 over y. And that is the x component, so times I hat. Then the y component is Coulomb's constant times the density divided by y times L over square root of L squared plus y squared and times j hat. And the unit is newtons per coulomb.